Hello, everybody, and welcome to another web talk from the Inside Innovation series organized by the Cockrell School of Engineering at the University of Texas at Austin. My name is Eloisa Acha, and I will be moderating today's talk. The topic for today is important and timely. We will be learning and discussing the latest on improving disaster preparedness and recovery through data. Joining me today, we have three distinguished researchers working on various aspects of the disaster cycle, and each one will first share highlights about their research and their work through a 10-minute presentation. After those three presentations, we will have plenty of time for questions and answers, and we invite everybody from the audience to use the chat box in the window and submit your questions as we go. Now with that, I would like to introduce our first panelist. Clint Dawson is the new chair of the Cockrell School's Department of Aerospace Engineering and Engineering Mechanics. He has been a professor at UT Austin for nearly 25 years and leads the Computational Hydraulics Group in UT's Oden Institute for Computational Engineering and Sciences. His research in disaster analytics has been pivotal to the development of storm surge prediction models, positioning the university as a recognized leader in analyzing weather patterns and preparing cities and emergency response units for catastrophic weather-related events. Clint, thank you for joining us today, and I hand over the microphone to you.
Thank you, Eloisa. Let me share my screen. Can everyone see my screen? Okay. So yes, I'm going to talk today about storm surge modeling for hurricane response and mitigation. And I want to recognize the divisions of the university which I participate in. And that includes the Oden Institute for Computational Engineering and Sciences, where I'm the head of the Computational Hydraulics Group, as well as the Department of Aerospace Engineering and Engineering Mechanics within the Cockrell School. So first, I want to discuss what is storm surge. Storm surge, if you look at the definition in the dictionary, it's an abnormal rise in water generated by a storm over and above the predicted astronomical tide. Now, if you go out to the ocean, we often talk about mean sea level, and that's sort of the average height of the water on a daily tidal cycle. So, of course, we have high tides and low tides, and a high tide might raise the water level about 2 feet on a normal day, and a low tide would decrease the water level by about 2 feet. In the event of a storm surge, then the water level can rise several feet. For example, in this picture here, we see a 15-foot surge on top of mean sea level. And if that happens at high tide, then that 2 feet would be added to that 15 feet, and we would have a 17-foot storm tide. And then on top of that, we have waves, which can also cause additional flooding. So what causes storm surge is the wind. So when we have a hurricane, of course, we have this wind field that's rotating around the eye. And what happens is that that wind field produces a force which acts on the ocean. And as that force acts on the ocean, it causes the water body to rise. And if you're in the deep ocean, you wouldn't notice that very much because it might rise only a few feet. But as the water gets closer to the coast, as the ocean gets closer to the coast and the water gets more shallow, then you see this water starting to pile up. And as the hurricane makes landfall, then all that water gets pushed inland, and that's what causes the flooding. Now, you're probably familiar with what are called spaghetti plots. So if you watch the weather when a hurricane is approaching land, and these particular figures were during Hurricane Dorian, then you'll see these, on the left, you'll see all these lines that represent hurricane tracks from different models of the hurricane. There are many different models that are run, computer models that are run around the world that study hurricanes and weather in general. And so here you see about a dozen different models, and they're all pretty well aligned. If you look at the lower right corner of that picture, they're all pretty well aligned, but then as you get further out, they start to diverge from each other. So the National Hurricane Center, which is in Miami, Florida, and is run by NOAA, they take all of this information and they come up with what's called a forecast. And a forecast is released every 6 hours during the day. And so they collect all of this wind data, and from that data, they predict the track of the hurricane, the size of the hurricane, or the radius of the hurricane, as well as the intensity of the wind field. And so on the lower right, you see what the National Hurricane Center prediction would be. So you can see the track, you can see the category here is 4, and you also see what's called the cone of uncertainty. So as we get further in time, then we have less assurance of what the forecast is going to be. And so the Weather Service adds some what they call the cone of uncertainty, which means that they don't know exactly where it's going to make landfall. And it kind of coincides with where these tracks on the left are diverging from each other. Now, from the wind forecast, we can create a storm surge forecast. So computer models take the wind data from the National Hurricane Center, and they solve mathematical equations that can predict the water levels and the water velocities. And these computer models are called storm surge models. And they can be used for many purposes, including emergency planning, such as deployment of first responders or perhaps trucks full of food and supplies before a storm makes landfall. They can be used to order evacuations, determine evacuation routes, whether or not to open or close bridges and roadways, and for several other purposes. And my group at UT Austin has collaborated with a team of researchers across the United States to develop what's called the Advanced Circulation Model, or ADCIRC. So ADCIRC is a computer model that's been developed over a period of about 30 years initially by researchers in the US, but also by involving researchers in other countries. And it solves the shallow water equations, which are mathematical equations that describe the water elevation and the water velocities during a storm. And we use numerical algorithms to solve these equations. It's widely used for storm surge modeling as well as for other purposes, and government agencies that utilize it on a daily basis include NOAA, the US Army Corps of Engineers, and the Department of Homeland Security. And if you're interested in more details, you can click on this link that's in the presentation, which will be sent out to you, and you can read more information about the code. Now, to be able to generate storm surge forecasts, we have to run the code on high performance computers. And we utilize the computers at the Texas Advanced Computing Center, or TAC, which is the computing center located on the UT Austin campus. And TAC operates 3 supercomputers that we use, Frontera, Stampede 2, and Lone Star 5. Frontera is the newest supercomputer at TAC, and it's one of the top 10 supercomputers in the world. So out of this code, we've developed what's called the ADCIRC prediction system. So this is a framework of computer models as well as ADCIRC that completely take the wind forecast and run a complete cycle through the storm surge prediction. And so the ADCIRC prediction system, or APS, is operated in real time during a hurricane. It's operating as we speak for Hurricane Zeta, which is going to hit Louisiana either sometime later today or tomorrow. And it's run by the University of North Carolina, Chapel Hill, LSU, and my group at UT Austin, as well as in partnership with TAC. It's operated for all hurricanes threatening the US coast, and emergency managers such as those in the Texas Division of Emergency Management or in the Louisiana Division of Emergency Management, they use the results of ADCIRC for decision-making as storms approach landfall. And results from the prediction system are posted at a website, which is hosted at LSU, and it's given here. The link is given here. And if you go to that website, you can see an image such as this, which is an image that I downloaded yesterday for Hurricane Zeta. And what you see this is coastal Louisiana. Here's New Orleans. You see the predicted track of the hurricane, this black line. You see the cone of uncertainty. And the colors here represent the predicted storm surge. So the water levels in feet above mean sea level. So right now, at least as of yesterday, it looks like the major storm surge is going to happen along the Mississippi, Alabama coast. And these results are updated every 6 hours, and you can go there and look at the results and actually move around within in the image, and there's a lot of data there. In addition to predicting storm surge, we can also use AdCirc to look at storm mitigation strategies. So these are more long-term studies where we want to design a storm surge protection system, such as a system of levees and seawalls. And currently AdCirc is being used to design a new protection system for the upper Texas coast that goes from Houston and Galveston all the way up to Beaumont and that area. AdCirc was used in the last decade to design the new $20 billion New Orleans surge barrier, which has been in operation now for several years. So I want to end by just commenting on the importance of basic research. So computer models such as AdCirc can save lives and communities, but they wouldn't exist without the generous support from taxpayer-funded basic research through federal and state agencies. So I just want to acknowledge the agencies that have given financial support to our group and to other groups for the development of this code and the research that we do with it. And that includes the National Science Foundation, the Army Corps of Engineers, the Office of Naval Research, the Department of Homeland Security, NOAA, the Texas Advanced Computing Center, the Texas Division of Emergency Management, and the Houston Endowment through Rice University. So thank you.
Thank you, Clint. Now, before we move to our second panelist for today, we want to remind everybody to type in your questions in the Q&A window on the bottom side of your screen on the chat window. So our second panelist today is Erhan Kotanolu. Erhan is Associate Professor in the Operations Research and Industrial Engineering Graduate Program in the Cockrell School. His current research focuses on integrated humanitarian logistics, including event mitigation, preparedness, and recovery decision-making and optimization, particularly for hurricanes and other extreme weather events. He works to combine predictive science-based models with prescriptive stochastic optimization models to increase disaster resiliency. Erhan, I hand it over to you.
Thank you, Eloisa. Hi, everybody. Actually, Eloisa made a very nice introduction, so I will share my first screen and then start presentation. So here you go. Can everybody see it? All right. So yes, so my research focuses on advanced model-based decision making. So the idea is in there is, how can we make critical decisions based on models, data, and algorithms? What that means is that we apply our methodologies from operations research and industrial engineering to different kinds of decision-making problems, including disaster decision-making. So given today's topic, we focus on hurricanes and other heavy rainfall events, but we can apply these methods to other disasters or situations. So hurricanes devastate our infrastructure and communities, when they hit. Actually, it is surprising and unfortunate how damaging they could be, given that they are relatively predictable events. I give some examples in here in terms of the hurricane's impacts. Depending on the extent of the event, the infrastructure, or the locality of the hurricane, federal, state, local governments, other agencies, utilities, companies, and even people, individuals, they have to make decisions, allocate resources before, during, and after the hurricanes to save lives and property. There is a relatively formal term for this called resilience decision-making cycle. So that is basically what I show in here. We try to make what we call mitigation decisions, mitigation plans well before the disaster. These are basically long-term hardening of the components, or as Clint was showing, the storm surge mitigation picture that he showed, that is basically an example. And then we try to prepare ourselves just before the disaster or the hurricane. We preposition crews, spare parts. We basically brace ourselves for minimum damage and quick recovery. And then during the event, we respond with emergency operations and rescues during the disaster. And then right after the disaster, we try to recover as quickly as possible to go back to normal. We fix things, we provide temporary housing and whatnot. And then we are back to the beginning, which is mitigation again. Typically, state, local agencies, utilities, companies, they look at the maps, they look at the images to deploy resources to make decisions in these phases. But they are mostly done in an ad hoc fashion. Even if they are based on tools and models, the decision-making side is not well connected with the prediction side. And plus those prediction models, as Clint was mentioning, they are not perfect. They have their own inaccuracies, basically. So what they usually do is they basically look at those kinds of maps and images, assuming that that is what is going to happen, and then make their decisions accordingly. So we need better tools in terms of decision making, and we need to integrate the prediction and decision making side of the problem. So our approach basically accepts the fact that our prediction models are not perfect. We integrate the outputs of those prediction models as potential scenarios into our decision-making models. We integrate them basically. And then our models quantify the uncertainty and associated risk and makes the best decisions accordingly. So just to show you an example, of our approach, where, how it is basically done. For hurricanes specifically, we incorporate the uncertainty in track, size, and intensity. We simulate the impact via flood models as if a specific track, specific size, and specific intensity of the hurricane will happen. We repeat this simulation many times with different track size and intensity combinations. And then these outputs of the simulations, they become our flood scenarios. We overlay our infrastructure, communities, our households, and whatnot, basically where things are over these scenarios, and we capture the impact on the infrastructure and communities in our scenarios. Then the magic happens. The latest methods in our field, OR and decision analytics, can quantify the uncertainties in these scenarios and solve the scenario-based model to produce best mitigation, preparedness, and recovery decisions. Mitigation and preparedness decisions are plans for resource allocation before the event, and recovery plans are for after the event, and they are scenario specific. So pre-event plans are chosen such that you are protected as much as possible from potential impacts, and you are set or ready for a successful recovery after the event. The good part of these models is that your recovery plans for specific scenarios as contingencies are ready if a specific scenario is realized after your basically pre-event plans. I give you basically two examples in here, two specific and ongoing examples from our live research. Here, we first focus on healthcare infrastructure. Basically we try to evacuate patients and residents of nursing homes before hurricanes in case these facilities are at risk for flooding. Excuse me. are at risk for flooding or power loss. We again, like I said, consider explicitly the uncertainty in hurricanes' path, size, and intensity. We use the flooding scenarios, and then we optimize the staging areas to position our ambulances and ambuses, and then we route the patients from sending hospitals that are at risk to receiving hospitals that are safe. And all of this is done in an integrated fashion. We currently have a prototype version of this framework for the Houston area in collaboration with an agency called SATRAC, Southeast Texas Regional Advisory Council, that is basically responsible for these operations before the hurricanes. My next example is from the power grid. That is a brand new project, basically, that is in development. This is called, well, we basically look at the mitigation, preparedness, and recovery phases of the decision-making process. Again, the events are hurricanes or heavy rainfall events. And this basically, the image shows the full cycle, how we go from weather forecast all the way to resilient operations that are done for specific hurricanes, upcoming hurricanes in the short term, or we can do this over multiple seasons, what we call midterm planning, or even long term, especially if you want to include the impact of climate change on hurricanes, frequency, intensity, and whatnot. You can basically look at your infrastructure and see what you should do in the long term over multiple years or decades. Future work in this area, I highlight two of them in here. There's a non-trivial problem in terms of how we allocate resources between mitigation and recovery. You would like to mitigate and prepare yourself because time is on your side, but the impact is uncertain. At the same time, you would like to recover. You would like to allocate resources for recovery because you'll know exactly what happened. But every recovery action is so expensive. So how would you do that non-trivial allocation of your resources, your dollars between mitigation and recovery? The second problem is a little bit more challenging, and it's about basically focusing on what you should do to adapt your infrastructure in the long term. This is just a picture of last year's hurricanes, where 3 hurricanes, starting with H, I, and J, were happening at the same time. Scientists predict that these things will happen more and more often, in the upcoming years. This year, we ran out of the English alphabet. We are now in the Greek alphabet to name our storms, basically. So we can do business as usual. We can respond to these disasters, with our best efforts in the resilience management cycle. But maybe we should ask this other question: how should we design our infrastructures of the future for resilience? So this is basically questioning the overall design of our infrastructures to make sure that not just we minimize cost, not just we focus on where we build things and whatnot, but ultimately we build it for resilience. With that, I would like to thank my sponsors and collaborators, and I will be available for questions and comments at the end. Thank you.
Thank you, Orhan. Now, last but not least, allow me to introduce to you Gordon Wells. Gordon Wells serves as the program manager for the Mid-American Geospatial Information Center located at UT Austin's Center for Space Research, where he supervises the operation of the dual X-band direct broadcast satellite receiving station. Since 2003, he has served as the member of the Texas Governor's Emergency Management Council, supporting the state's preparedness and response programs for natural and man-made disasters. Thank you for being here with us today, Gordon. The microphone is all yours.
Thank you very much. It's nice to visit with everyone today. I do have something to show you. And I think somebody needs to release the screen for me. Cool. Thanks. All right, what are we looking at here? This is the State Operations Center, which is deep underground beneath the Department of Public Safety headquarters. in North Austin. And this is where the state gathers their coordinators and directors who are going to send resources into the field in coordination with the federal assistance that we're receiving. When a major disaster is approaching, whatever it might be, it could be a storm, it could be a large wildfire, could be an inland flood, or it could be a man-made disaster of various sorts. But I have a position there and have since 2003 been the University of Texas representative to the Governor's Emergency Management Council. And I'm working in this portion of the State Operations Center with the National Weather Service and with some of the other folks from NOAA that will come down for major events. And we form a little predictive cell that advises the state agency and federal agency coordinators who have field teams and various other operations in progress. So we're giving them guidance about the threat environment. That's my role. And the important thing to know about this is that each one of the people that you're looking at in this photograph will have a very different question to ask according to their concerns of their agency. We may have the same information product to give them, but we're going to need to address their specific questions about what the circumstances are and what the threat is for their individual areas. So again, we're dealing with a number of different agencies, all attempting to network together to come up with answers to questions that you don't know are going to arise during a major disaster. This is a very interpersonal operation. The state has a lot of resources, but you cannot always predict in advance exactly how those resources need to be deployed. So we're going to be using forecast modeling of the kind that Professor Dawson was talking about to give some guidance and information to the state, to state leadership, as well as to the Director of Emergency Management and all of his personnel, and then to the individual state and federal agencies who all have different roles to perform. So turning back to what Professor Dawson was just showing, I wanted to give you a couple of examples here recently, this year, about how that guidance was used. This goes back to Hurricane Laura. And at that stage here, we're looking at the storm surge, which is fortunately mostly on the Louisiana side. The high winds were also focused there. The main concern for the state was in this area around Port Arthur, where there is a lot of new infrastructure and other sort of underbuilt levee systems that they were fearing might be overtopped by Laura. However, when the storm shifted track and made landfall in Louisiana and followed that track inland, shown here, the winds were actually blowing offshore. And that meant that the storm surge did not come up the Neches River and overtop those levees. And in fact, the state did not have to dedicate resources to evacuate Port Arthur or to do a lot of search and rescue there. We could show them a day ahead of time that so long as the storm was on its current track and did not shift, that they did not have to dedicate additional personnel into that area. This is really good guidance for the state to know. They need to know how they're going to put their forces out in the field so that they can respond quickly and adaptively. And the groups that I'm working with specifically are Texas Task Force 1, the search and rescue teams, and they had groups up in Lumberton, north of Beaumont, at Ford Park in Beaumont, and also in Port Arthur, the southwestern part of Port Arthur. This is a really great guidance product that we can provide to them. I was working with the director of Texas Task Force 1 and talking with the field teams. This is guidance that comes out of the ADCIRC prediction system, and it tells the folks in the field, when are you going to have high impact winds? This is only the winds that we're talking about here. They've already seen the graphics for the storm surge, but what they need to know is where can we get to a very safe location and know that we have to wrap up our search and clear operations before the storm hits. How much time do we have before tropical storm force winds hit and then the hurricane winds? And then on the other side, as the event peaks and the eye passes over the area to the east, the winds shift and then they decline. they need to know when they can go out and do the search and rescue. And they cannot do that in high winds with the boat squads. They need to have winds that are basically below tropical storm force. So this graphic really gives them guidance and planning options where they see the timing and the magnitude of the event that they're about to have. And we've done this in several areas, not just Texas, but in North Carolina, where all the national teams were using this product in New Bern and places like that. So shifting focus now, after the storm strikes, we shift our attention to doing documentation of the damage and the extent of flooding. And as a Center for Space Research, we do that with satellites and also with aircraft. And this is data from a NASA Jet Propulsion Lab radar system after Hurricane Harvey, showing the flooding that was occurring in the Brazos Basin, actually areas where we have a lot of prisons. The areas in blue and purple are flooded. This is a radar image with about 3 different polarities, which is excellent for showing areas that are on dry land and areas that are wet and areas that are underwater. When we were receiving this data, we had search and rescue teams in Rosharon that I was talking with in the field, so we could give them very rapid guidance on what was happening. I want to shift to this next scene. This is a Russian satellite image that was taken about 30 minutes afterward. We're connected with the international consortium that provides International Space Agency satellite data to us. So this is what you would see visually, all of that muddy water on the left-hand side of the graphic coming down the Brazos. Compare that with the identical scene in the radar. You have these two together. You've captured the high magnitude part of the event and the full extent of the flood, and you have 2 different ways that we can combine to show what was flooded and what wasn't. So that is really important information that can feed back into the models that Professor Dawson is working on to show that we're capturing all the inland details of what high rainfall plus storm surge and local river flooding will produce. Gives us validation. We're also working with a lot of aircraft. I get to task the Civil Air Patrol and also the National Guard, their Air National Guard assets, to go out and take photographs. This again is during Hurricane Harvey, just after it was over. Each one of the dots on the photograph, the image here is an individual photograph that was taken of the event. We had 342,000 of these photographs made. So really excellent ways of documenting just how high the water got here in a place like Rose City on the eastern side of the Neches River from Beaumont. We can capture all of these details and get the full documentation of all that occurred during a high magnitude event of that kind. So this helps us in recovery, where we know the characteristics of these historical events and we can begin to plan for something that would be of the same character and magnitude, or maybe something that would be worse. We know what happened before. The radar satellite data is really paying off in showing us these heavy flood events that we're getting basically from just having a lot of rain in one location very rapidly. So this is from Tropical Storm Imelda. It did not produce as much rainfall as Harvey, but it still got up to 40 inches. And in these areas of northeastern Houston, all those areas in blue are flooded at the time this image was taken. And you might notice that the river systems are not transporting water to any degree. There is so much water that is basically trapped on the landscape. It's on a very low slope, so it is basically just obstructions in the way infrastructure is laid out. The highways are more barriers than conveyances here, and you get local ponding and a lot of flooding. This was a pretty dramatic event actually for northeastern Houston. Just an example of how rapidly we can get a full picture of what is underwater during an event like this. And finally, we do disaster analytics ourselves. We go back and look at a lot of the statistics from the insurance records and various other representations of where damage has occurred. Believe it or not, we've had properties in the state that have been either heavily damaged or destroyed. on more than 10 occasions. And we're paying the insurance for that through the National Flood Insurance Program, and have now provided several times the value of that property in the insurance losses that have been reimbursed to the person that owns that policy. So we need to look at this in detail in the future and figure out, are we going to keep doing this? Are we going to keep building in areas that are repeatedly flooded? Just something to keep in mind in the future. And finally, the tools that I've been showing you that are used to relay this information, the different emergency management coordinators around the state and the counties and the cities, as well as the state agencies, they're all very accustomed to using tools that we have developed for various disasters. So when we began the COVID-19 episode here that we're all living through, I've been working with Professor Lauren Ansel Myers and her group, and part of the UT Pandemic COVID-19 Consortium. And we have taken the data that they're producing as forecast, and we're taking the observations, we're putting them in the same context and web services that we use normally for other major disasters. And this is a very good way for the emergency managers to get to those details day by day and seeing what's happening in their area. You've probably heard about El Paso recently. They are on a very steep incline. These are the hospitalizations that have occurred just in the past few days, and you can see how that relates to the earlier parts of the event. Unfortunately, there are lots of other areas in the state that are moving toward this kind of very bad peak, and we will need to be aware of that moving forward. So that's all I had to say today to you, just to give you some background on how we work with the state and the state agencies during these major events. Thank you.
Thank you, Gordon, and thank you to really the three panelists. The research that you do is particularly relevant for Texas, since our state experiences by large margin more major disasters than any other state, which carry not only an economic toll, but also a human toll. So thank you so much for what you do. Now let's transition to the question and answer section. And we want to invite our audience to ask any questions to our specialists, anything that you were ever curious to learn about disaster planning, response, and recovery. And thank you also to the audience that pre-submitted some of the questions. So what I will do is I will go through some of the questions that we've received from our audience first. And there was a question that probably on everyone's mind is important. And maybe, Gordon, this is something that you can help shed some light. Can you help tell us how many days do emergency managers have to prepare for a hurricane making landfall?
It depends, of course, on whether this is an Atlantic storm or a storm that forms in the Caribbean, or whether it's something that forms in the Bay of Campeche and the Southern Gulf. The latter storms, the ones in the Southern Gulf, may give us only 72 hours of preparation time. If you look at Harvey, Harvey disintegrated, passed over the Yucatan, reformed, and from the time it reformed, we had 66 hours before landfall of a Category 4 storm. We hope for more time, but historically we've had much less. A lot of the planning is done on a 120-hour timeline, and I've done those timelines for the state since 2004. And I've tried to encourage the state, don't think about 120 hours. We're going to have to compress these timelines on almost every event. And finally, I think Harvey sold them on that idea. It only took me a decade to get the message across to them that they shouldn't be thinking about a 5-day timeline for the arrival of a big storm.
And maybe this second question from Matthew could help shed light on potential opportunities for improving that response time. Have you found any value in data from newer companies offering daily CubeSat imaging?
Yes. Planet Labs and others. I'm very excited about the commercial groups with small sats that they have different strategies of how they're doing global coverage for different purposes, mostly commercial operations. And it is adaptable for emergency response. We've done wildfire work in Paraguay from Austin using the Planet Labs, Planet Doves satellites as well. So it's a very effective system. They need to reduce some of their latency and time of delivery, but I think they're getting over some of those hurdles now. And gosh, the more small satellites we have imaging, the more opportunities we have to respond quickly.
Thank you. So now there's a question around flood damages. And the question is, there's actually several questions. So how are flood damages measured? And then the second part of the question is, how are they distributed? How are those flood damages distributed among the various domains of infrastructure? So say energy grid versus residential or economic capacity. So what's kind of the difference in your experience? And I don't know if you want to start, Clint.
I think Gordon should answer this question because.
Okay.
But I don't want to answer all the questions. Okay.
I'll pitch in if you start.
Yeah, Gordon, why don't you, because I know that you have to do a damage assessment for FEMA right away, right?
Yeah, we have a pretty hard timeline because we have to go to Congress and try to get relief money back to the state as soon as possible. So we're using the aircraft data to look at the distribution, how far afield damage has occurred. We also look at it for the magnitude of damages and for the style of damage. And there is some quick modeling that we can run with the Army Corps to determine the dollar damage estimates over a broad area like a county-wide area or larger. And we've been doing that since Hurricane Ike. It's been pretty successful. Harvey was just epic and very difficult to calculate because it was flooded everywhere in pockets where we would not have potentially predicted with a more normal event, if there is such a thing anymore.
Yeah, well, what I would say is that, especially with Harvey, the damage was distributed both, on the energy infrastructure and residential areas. I have some statistics on Harvey's impact on the power grid to motivate the energy infrastructure project that we have. Of course, power lines, poles, and transmission assets, but even the substations that are supposed to be somewhat hardened against flooding. I believe there were 15 or so flooded substations during Harvey. So when the event is like that, then unfortunately, even the places that we think as safe are vulnerable, basically. Yeah.
And it depends a lot on where the hurricane makes landfall.
Yep.
I mean, imagine a hurricane hitting downtown Houston versus a hurricane hitting the coast, along the coast where there's very little population density or even, communities. So
Correct.
it can vary a lot with the hurricane. And some hurricanes are more wind damage hurricanes. I think Laura was a big wind, and maybe Gordon can correct me if I'm wrong, but Laura did a lot of wind damage, not as much surge and rainfall. Mm-hmm. And Harvey, of course, was a huge rainfall event.
Correct.
And then Ike and Katrina were huge surge events. Mm-hmm. So.
We also had, thank you for the comments. We also had one of the pre-submitted questions about the review cycle. So what is the review cycle, if any, on the previous risk models to improve the implementation of risk treatments to either reduce the likelihood or impact of issues from natural disaster events?
I would say ongoing. I think that after every hurricane, we try to look and see how well we did in prediction. And we go back and do studies to see if we actually matched data. But the agencies that we work with are continuously improving their models. And so there isn't in terms of a sort of a planned cycle, I would say I don't know that exists, except perhaps they do have a plan for replacing equipment, replacing computers. But as far as replacing software, the software undergoes continuous improvement.
And Arhan, do you have a perspective from the logistics side on the same question of how often perhaps utilities or some of the organizations that you work with review those
Yeah.
models, those plans.
On the energy or power grid side of things, we are in contact with a couple of utilities, especially in and around Houston, Entergy and Centerpoint and whatnot. We are just learning what they have been doing, until basically, we do our project, we have our tools available for them. My most experience is really with SATRAC, who is doing the patient evacuation before hurricanes. And as far as I know, they basically use what comes out of the bunker, if you will, from Gordon Wells' group to say, well, okay, these are the hospitals that are at risk, and we have to evacuate them. They deploy resources like that, and then of course they learn from every evacuation. As far as I know, the last major evacuation that they did was Harvey, and they learned quite a bit. But our understanding is that they were doing it basically one hospital, one patient, one vehicle at a time, basically routing. And our model is trying to do all of that basically in one shot, hopefully helping them speed that decision-making cycle. And hopefully we can incorporate the data from learned events into the model very quickly so that it is ready for the next season if something like that happens again. I think there is no reason for us to not incorporate. There is no reason to not to incorporate the what we learn from an event until the next event, because we can quickly learn and then incorporate that into the model once we have the basic structure.
Great, thank you. So we have another question from our audience. Are there efforts to utilize localized climate change models in your disaster planning and mitigation operations? And if so, can you talk about some of the benefits and limitations involved?
Well, yes and no. Right now, I would say, at least from my perspective, the climate change, the changes that we make to account for climate change to the model are pretty primitive. For example, we'll just assume that sea level is going to go up a certain amount, and we'll just raise the ocean, by a foot or 2 feet. We'll look at different scenarios. So if the ocean goes up a foot, 2 feet, 3 feet, then what's the impact? But I'm not sure that it's that simple, because if the ocean rises a foot or 2 feet, then we start losing barrier islands. It changes what the coast looks like. So you can't use today's coast and then just assume the ocean goes up a foot, and that's what is actually going to happen. So I would say that's still an active and future area of research about how to really scientifically incorporate climate change into these models. That's my opinion.
Yeah, NOAA has recently reviewed the high rainfall events in Texas. They've issued a NOAA Atlas 14, and it has really changed the perspective on these high rainfall events, the amounts and timing of those events for Texas cities. I think Austin's major event went up by 3 or 4 inches, and Houston went up by 6 inches or so on top of their previous threshold. So all of that is beginning to be taken into consideration. However, our state climatologist, John Nielsen Gammon at A&M, has shown from the Harvey data that we may be still underestimating by a considerable margin what the highest magnitude might be. He's looking at 80-inch rainfalls rather than 60-inch rainfalls over places like Nederland and the southeastern Texas that got hit by Harvey.
Yeah, if you Google Atlas 14, or the city of Austin has updated flood maps. If you live in Austin, you might want to go check this out to see what your flood risk might be in the next few years, because it's going to affect your property may now be in a floodplain where where it wasn't before. Mm-hmm. I know, because I live in a floodplain. Believe it or not, as hard as that is to believe, my house is in the Waller Creek floodplain. And so, and the map has changed. The new map makes my property even more in the floodplain than it was before. So, which is a bit upsetting.
So we have another question, and Gordon, you touched on it a little bit during your presentation. Erhan, I'm sure you'll have some input. The question is, what is the effect of hurricanes for those cities that are a little bit more inland? So Jose remembers that during Harvey, various cities were mobilized to welcome climate refugees. So can you speak about how these operations may be improving during our pandemic era?
Yeah, I'm trying to get the exact gist of the question. If you're talking about the physical impact to inland cities, of course, hurricanes can cause damage very far inland, especially a windstorm from a hurricane, and also the tornadoes that can spin off on the margins of it. And the other impacts that we see, especially when we have Louisiana hurricanes, is that we have an outmigration from Louisiana of evacuees that we have to work with. And our state mass care coordinator only recently finished working with a lot of the Laura evacuees from the Lake Charles area and other areas in far western Louisiana that came to Texas. And all of them, many of them are going into state shelter operations and things where we have to do the provisioning along with the Red Cross.
Yeah, and I think, you know, more inland rainfall is another, you know, I guess disaster that you have to watch out, and flooding that is caused by rainfall. But of course, shelter operations, you know, or basically moving people, especially moving vulnerable people without cars or whatnot, it's a large logistical operation, and I don't know. I'm not in the loop to say, well, this is how the state or local agencies do, but you know, our models for evacuation, patient evacuation logistics could help along those lines too, if needed. But it's a difficult question, you know, and especially with the pandemic, you cannot just, you know, put 10,000 people in a stadium and then call for the day. I don't know how long we're going to live with the pandemic and this issue of social distancing and whatnot, but ultimately it's a challenge because now the resources cannot stretch as much as we think. You know, we have to use them even more carefully. So.
Mm-hmm.
So Gordon, how did you handle Laura evacuees with the pandemic going on?
Very much the same way we did for some of the earlier Texas evacuations. One of the things you have to do is you're not going to get 40 people on a long distance coach. You're going to get about 20. Yeah. So you cut your resources in half in terms of how many buses you're going to have to allocate. You'll have to double those just to get transportation done. Fortunately, there was a lot of accommodation that was available in hotels and that would not normally be available, but because people aren't traveling, they put many evacuees in rooms like that rather than in congregate settings, arenas, convention centers, things of that sort. So that has been a major issue to think through, just all of the logistical details of how you do an evacuation in the middle of a pandemic. Just bringing people to a transportation site and having that organized and laid out. State Guard does that. They do a terrific job. And all of that is visible as they're scanning evacuees on board a coach, scanning the coach. The coach is tracked by GPS. So we don't lose evacuees in Texas once they're within state care. But the speed at which it can be done and the numbers that can be done, that presents a real challenge.
Also, our audience is asking for any websites or materials, resources where they could learn more about disaster relief issues. Do you have recommendations? Or a couple of them that they could look up?
I would look at the Texas Division of Emergency Management, their website. And the governor's office is usually pretty good about putting out messaging on Texas and disaster. But they would probably be referring back over to the Division of Emergency Management. So it's a loop there. Red Cross is always a good site too. I mean, they're dealing on it all over the world with different styles of disasters.
Great. So you also all of you alluded to how the storms are intensifying at increasingly rapid rates. What, if any, new technologies could we leverage to get ahead and prepare for these events? Can you each comment on a particular technology or up and coming area of research that you see promising?
Well, one thing that we've really been concerned about, especially since Harvey, is what we call compound flood events. So this isn't necessarily new technology, but it's new simulation capabilities that are needed to account for what happens when you have combined storm surge and heavy rainfall and they interact with each other. And we saw this quite a bit in Hurricane Florence in North Carolina, where you had storm surge and then you had rainfall coming down through various watersheds, and they met each other in the middle, so to speak. And so there was flooding from both ends. Also, I think in terms of research, there's a lot of connections now between the physical type of modeling that I do or other people do and the social impacts of those models, which, you know, we're continuing to try to make those connections, and also how do we present our results to the public? How do we work with people like Gordon who have direct contact with local officials and just the general public to convey the information that we're producing in a way that is understandable?
On my side, I can maybe mention two things that we are trying to do apart from the future work that I cited in my presentation. But one is cascading impacts, right? So you model the power loss that might happen due to hurricanes, but then that might affect a nursing home that is losing power, and then AC is an issue, right? And that at the same time you're trying to evacuate. So those kinds of cascading hazards, modeling that, and then not just looking at part of the problem, but looking at the overall problem, overall impact that might be a result of some other risk, and making decisions accordingly, right? That's a challenge. For now, we are still doing an integrated decision making, but still we are not including that cascading impact. The other one that is picking up speed is equitable decision making. How do you make sure that your mitigation, your preparedness, and your recovery projects, that are done, especially by state and local governments, they are responsive to vulnerabilities, social vulnerabilities in the communities, and they are also equitable overall. So, but we are always in the search of, good coding, good algorithms, good models, more efficient models and algorithms, so that we can make these decisions as fast as possible.
Faster and bigger computers are always important.
Yes.
Always. Yeah, I think that the social vulnerabilities are really important. We need to look at that landscape in the same way that we're able to generate the physical impacts, and know in advance when you overlay a physical impact on top of a particular sociological setting, demographic, socioeconomic, et cetera, that the outcomes are going to be different according to location. We need to know that in advance to respond more effectively.
Great. Well, thank you. I want to thank again Clint, Erhan, and Gordon for the discussion today. It's about time for us to wrap up. So thank you again for the important contributions of your research towards our resiliency to disasters, and it affects all of us. So thank you so much again for the work. Also, thank you to the audience for joining us today. You will be receiving an email, follow-up email with a link to the recorded event. Thank you again for the time. Stay safe and hook 'em.
Thank you.